We can predict how functions are going to look through knowledge of function transformations. Function transformations are very powerful because once you understand function transformations, as long as you know what the basic function looks like, you can always transform it and look at what the new function will look like. So it only requires you really understand the parent function, a handful of basic functions, and then from there you're able to graph whatever function you want and find points on whatever function you want. As always, feel free to jump to a particular portion of the video using the timestamps in the description if there is a specific topic that you're wanting to know about. Let's talk about vertical shifts first. So in order to discover why a vertical shift works, it's a lot of times helpful to first rederive by hand why a rule works the way it does. So if, for example, I want to know how the absolute value of x minus 1 looks, we're going to compare this to the basic absolute value function. So remember from last time that the basic absolute value function was this nice beautiful v that had a vertex at 0, 0, and then would go up 1 over 1 each time. So for example, has a point at 1, comma, positive 1 and at negative 1, comma, positive 1. And let's see how changing y equals the absolute value of x looks different if we just subtract a 1 on the outside as well. I challenge you to go ahead and pause this video and fill out this table yourself and see if you can go ahead and see what the pattern is. If we're filling out this table, absolute value of negative 3 is positive 3 minus 1 is 2. Absolute value of negative 2 is positive 2 minus 1 is 1. Absolute value of negative 1 is positive 1 minus 1 is 0. Absolute value of 0 is 0 minus 1 is negative 1. Absolute value of positive 1 is 1 minus 1 is 0. Absolute value of positive 2 minus 1 is 2 minus 1 is 1. Absolute value of 3 minus 1 is 3 minus 1, which is 2. And you'll always notice this repeating pattern around the vertex in general on absolute value graphs. So if we plot this, he ends up, and actually let me change the color on him. If you are colorblind, I do apologize that me changing the color doesn't make a huge difference, but I will label each. So in this color we have the new graph labeled, and then above it we have the original. So by minusing 1 on the outside, how does our new graph transform from the original? Well, this made him move down 1. Every single point, the x value stayed the same, but the y value moved down 1. And in general, that's how vertical shifts work, is if I add or subtract a number on the on the outside, x's stay the same, and y's move in the same direction as the sign on what's on the outside. So if I have the absolute value of x minus 1, that means since that minus 1 is on the outside, we go down 1. If I have the absolute value of x, I don't know, plus 100, that means that I would move up 100. And that's exactly what this is showing here. So even if I didn't know that this graph was a cube root, once I see this graph and see that it went plus 1, that means I know that the point 0, 1, for example, moves up to the point, the point 0, 0, for example. I was getting ahead of myself here. This origin is the point 0, 0, moves up to the point 0, 1. We know that this other point here at 1, 1 moves up to the point of 1, 2. We added 1 to the y value. Similarly, this point down here at negative 1, negative 1 went up 1 to negative 1, 0, because negative 1 plus 1 is 0, and that's true all along the entire graph. So we can create graphs by just knowing their vertical shifts. So if we want to transform the original absolute value of x by vertically shifting up 2, I want to pick out a few points that I'm going to vertically shift up to. So the vertex is a point I should always be moving, and then at least one point to either side. So we originally have the point 1, 1 over here, and negative 1 over here, negative 1, comma 1 over here. So that should move to the points 0, 0 should move up to 0, 2. That's shifting the y value up 2. 1, 1 should move to 1, 3. That's adding 2 to the y value, but keeping the x the same. And similarly, negative 1, 1 should move to negative 1, 3 because I added 2 to the y value. So plus 2 on the y, keep x when we're looking at individual points. And now that's our nice, beautiful new graph. And what would the actual equation look like? It would just be y is the absolute value of x with a plus 2 outside our absolute value signs. That transformation looks a little different if what we're looking at is on the inside. So just for, again, looking at how it changes from the original, I'm going to write down the original here. Of course, I made that last line a little bit messy. I'm going to fix that. So this is the original. And then I want you to go ahead and pause the video and see if you can derive both the graph for and the rule for what this new one will look like. So if now that minus 1 is on the inside of the absolute value, in terms of order of operations, I do that first. So negative 3 minus 1 gets me negative 4. Absolute value becomes positive 4. Negative 2 minus 1 gets me negative 3. Absolute value gives us positive 3. Negative 1 minus 1 gets us negative 2. Absolute value gets us positive 2. 0 minus 1 gets us negative 1. Absolute value makes this positive 1. 1 minus 1 gets us 0. Absolute value is still 0. 2 minus 1 gets us 1. Absolute value is still 1. 3 minus 1 gets us 2. Absolute value is still 2. So we can go ahead and plot these points. Negative 3, 4. Negative 2, 3. Negative 1, 2, 0. Ooh, I just misplotted that last point. That is not up to. Negative 1, 2, 0, 1. Then we've got 1, 0. Then we have 2, 1. And then we have 3, 2. So the new graph looks like this. So how did the original change to the new graph? Well, we moved to the right 1. Up and down didn't stay. Our vertex is still at y equals 0, but now instead of being at 0, 0, it's at 1, 0. So this moved to the right 1, which if you notice is the opposite sign of what's in here. So you move in the opposite direction, left and right. That's how any transformation on the inside here works. Go ahead and see if you can, for this one, first predict how you think it's going to move, and then actually fill out the table to see if that's how it actually moved. So the original, remember, looks like this. Starts at 0, 0, goes up 1 over 1 in both directions. And then since we moved the opposite direction last time, we may predict that we expect this to move left 2. Because instead of adding 2, we would normally think that moves to the right. We're going to predict, well, I think that means we would move points left 2, and then still move up 1 over 1 in both directions. And let's see if that actually pans out when we plug in points. So when we plug in negative 3, for example, negative 3 plus 2 gets us negative 1. Make it positive is positive 1. Negative 2 plus 2 is 0. Absolute value, make it positive, gets us 0. Negative 1 plus 2 gets us negative 1 plus 2 is positive 1. Make it positive is still 1. 0 plus 2, 0 plus 2 is 2. Absolute value of that is still positive, so that's 2. 1 plus 2 is 3. Absolute value of 3 is 3. 2 plus 2 is 4. Absolute value of 4 is 4. 3 plus 2 is 5. Absolute value of 5 is 5. So we have points at negative 3, 1, still there. Negative 2, 0, still there. Negative 1, 1, still there. 0, 2, still there. 1, 3, still there. We have 2, 4, still there. And then we have 3, 5, which is indeed, if I continued our pattern, exactly where we would be. So if you recognized that this would be left 2, it was a lot faster just to move left 2 and then still go up 1 over 1 in both directions because we didn't change the slope. Or you could fill out the table and rederive that it looks exactly like that. And in general, that is how a horizontal shift works, is we indicate it with this f of x minus h because essentially you just move the opposite direction of whatever is inside the parentheses is inside the function. So minus 1 moves to the right, plus 2 moves to the left. We could do that with a function we haven't studied yet, really. So x squared, we kind of know how to solve quadratic equations like that, but we haven't really formally graphed them yet. That's during the last units. But we can use function transformations still to graph these, actually, if we already know what the transformation should be. Now, if you're going to do a quadratic, I would recommend pointing out a few clean points on the original. So we have 2, 4 here. We have 1, 1. Anywhere, I'm just noting anywhere where it actually is nice and clean. If, for example, I wanted to know over here at 3, that gets, well, actually, that's not messy. If I wanted to know like 1.5, that would be kind of messy. Let's keep on going. So we have another point here at negative 1, 1, and then we have one at negative 2, 4. So all of these, if I want to move horizontal left 1, that means you want to keep your y's the same and move x's left 1. So for example, negative 2, 4 should move to negative 3, 4 as our new point. Because I moved negative 2 left 1 to negative 3. Similarly, negative 1, 1 should move to negative 2, 1. I moved negative 1 left 1. 0, 0 should move to negative 1, 0. I moved to 0 left 1. 1, 1 should move to 0, 1 because I moved 1 left 1. And 2, 4 should move to 1, 4 because I moved 2 left 1. And then I just want to connect that in a nice beautiful U. You want to make it somehow clear that this is really more of a U shape and not a V shape. And this lowest point down here is also still called a vertex. So now we have a new vertex at negative 1, 0. What should his equation look like? Well, we're still going to put the transformation inside the parentheses, but for left 1, instead of saying x minus 1, that's x plus 1. We could double check that if we plugged in points, we get what we predicted. If, for example, I plugged in negative 3 plus 1 is negative 2 squared gets me positive 4. If I plugged in negative 2 plus 1 is negative 1 squared gets me 1. Plugged in negative 1 plus 1 is 0 squared gets me 0. So we end up getting the same points that we predicted. And if you have extra time, it's worth actually plugging in points that way. We could look at a parabola that's already been transformed to write what the function is. So here, what changed between these two parabolas? Well, here we moved right 2. So our vertex went from 0, 0 over here to 2, 0. It may be worth double checking that we didn't have any other transformations. We're going to get into stretches here in a moment. But the other points also seem to still keep the same relative slope to one another, if you will. Slope is maybe a little bit misused here since it's a quadratic. But for example, the point 1, 1 also moved right 2 over to the point 3, 1, just like we would predict from our right 2 observation. What would be our new actual function? Well, to go right 2, instead of adding 2, we're going to subtract 2 because it has to be opposite sign. And we could double check if, for example, I plugged in 2, 2 minus 2 is 0 squared, gets us the point 2, 0, just like I would predict. If we plugged in 3, 3 minus 2 is 1 squared, gets us 1, just like we would predict. We can also write tables using function transformations as well. And there we're really wanting to think about how we individually move particular points. So if we're talking about a vertical shift, we're going to be adding and subtracting from those y values. If we're talking about horizontal shift, we're going to be adding and subtracting from those x values. So here we have a table for a mysterious function. You know, it starts off at points like 2, 1, and then we have another one at 4, 3. Then we're already working a little bit off the page that there's like a 6, 7 up here, and we're wanting to look at what would a new table for g of x, such that it's f of x minus 3, look like? Well, what does this minus 3 on the outside do? It moves us down 3. So here, do we want to change the x values? We do not. So the x's should be the same. What about the y values? For the y's, we're going to subtract 3 from each of those points. So as I'm setting up my table, I'm going to do exactly that. So I'm going to initially keep all those x values identical because I didn't touch them. And then for g of x is equal to f of x minus 3, I'm going to take all those y values and move them down 3. And I can double check that physically on my graph, that if I move down 1, 2, 3, I expect a new point here, 2, negative 2. 1 minus 3 gives me negative 2. Keep on going. 3 minus 3 gets me 0. 7 minus 3 gets me 4. 11 minus 3 gets me 8. And that's exactly what I would expect, moving all of those guys down 3. And so this is our new table. We can do the same sort of deal for any horizontal shifts. So first, just pause the video and ask yourself, what kind of shift are we talking about here? That would be moving right 3. So we could even sort of sketch out that if I have the point 2, 1, for example, and I move him right 1, 2, 3, now I'm at the point 5, 1. So if you notice here for our x values, did those change? Yes, so the x's we're going to end up adding 3 to. So you do the opposite sign of here. And then for the y's, did those change? They did not. So the y's stayed the same. And that's exactly how we're going to set up our table. In a way, you're sort of working backwards and you're trying to figure out at what x value, when I subtract 3, do I end up at our original x value. That's kind of why this logic works. So if I plug in 5, 5 minus 3 gets me 2, and now I'm reevaluating the function at 2. That's really the idea of this working backwards when we're talking about transforming x values. So I'm going to keep all these y values identical. And then we're going to talk about which x values, once I subtract 3, get to the original. So I end up doing 2 plus 3 to get us 5, 4 plus 3 to get us 7, 6 plus 3 to get us 9, 8 plus 3 to give us 11, and that's our nice, beautiful table. Sometimes we have both vertical and horizontal shifts going on at the same time. And if there are no other transformations besides a dual vertical and horizontal shift, you can do them in either order. Just make sure you do both. So here, what are the two shifts that are going to happen here? So for the inside here, that tells us that we move left 1, because remember it's opposite sign. And for the outside here, that moves us down 3, because it's the same sign. And once I get more than one transformation going on, I like to actually just like explicitly write exactly how all my points are going to move. So if I have the point 0, 0, for example, to move first left 1, then second down 3. So to move left 1, that moves that 0 to negative 1. Then to move down 3, that moves the 0 on the y's down 3. So I have a new point in negative 1, negative 3. What about the point 1, 1? Go ahead and pause your video and see if you can predict where that will move. To first move him left 1, that would move to 0, 1, because 1 minus 1 gives us 0. Then to move him down 3 from there, 1 minus 3 gets us negative 2. So that gives us, and then I just rewrote transcription error, still at 0 there. So we moved left 1, down 3 for 0, negative 2. Now you could also kind of know how the absolute value graph looks like and know I'm still going up 1 over 1 in both directions once you've moved that vertex. And then for good measure, let's go ahead and move one more point. So what about the point -1, comma 1? First, if we move him left 1, he's going to be at -2, comma 1. Then if I move him down 3 from there, that's -2, comma -2, because 1 minus 3 gives us -2. And really, I'm still going up 1 over 1 in a relative sense in both directions. If you don't believe me and you want to more individually plug in some more points, feel free as well. And if you also don't believe me that the order doesn't matter, feel free to flip-flop the order and make sure that you get the same thing. But this is our nice new beautiful graph where we have moved left 1, down 3 on all of our points. We can do that with a more unfamiliar graph as well, so we can think about where has this new graph moved? What does that mean that that original graph must have been? And we can also visually see how the domain and range are going to move as well. So here, if this original graph was at 0, 0, and then let's say we initially from there also had a point at 1, 1, and another point here at 4, 2 for the square root of x. I really should have picked a graph that had that labeled, but believe me that those points are on it. You can also plug them in to double check. Square root of 0 is 0, square root of 1 is 1, square root of 4 is 2. That's how the original graph looks. How did this graph move to make this graph? Just what were the transformations? Go ahead and pause your video to list the transformations and write the new equation. So there were 2 transformations here. The point 0, 0 moved up 2, and it moved right 1. So there are 2 different transformations we need to write down. So if the original was f of x is equal to the square root of x, what's going to go underneath the square root with the x? That's going to deal with the right 1, so we should have a -1 underneath the square root. What about the up 2? That goes outside the square root. So our new function is y is equal to the square root of x minus 1, and I usually add a little line here to make it clear that I'm done writing things underneath the square root, and then a +2. What does our domain look like it is physically on our graph? That starts at 1 here, because we have a new kind of starting point at 1, 2. So it starts from 1 and goes to infinity. So if you notice, our domain also moved right 1. What about our range? That goes from 2 to infinity, because it starts at 2 on the y's and keeps on going up. So our domain and range also moved according to our transformations. The domain moved right 1, and the range moved up 2. Another common transformation is a reflection. And what we mean by that, we'll see here in a second. So here, if I have a negative on the outside, keep in mind that actually means I do -1 times the absolute value of x. So let's take a look at the original and then see how the transformed one looks. So if the original looks like this, starting at 0, 0 and going up 1 over 1 in both directions. Let me label that as the original. Let's take a look at our transformed graph. So if I do -1 times the absolute value of -3, well, the absolute value of -3 is +3, times -1 is -3. -1 times the absolute value of -2, well, the absolute value of -2 is +2, times 1 gives us -2. -1 times the absolute value of -1, absolute value of -1 is 1, times -1 is -1. -1 times the absolute value of 0, the absolute value of 0 is 0, times -1 is still 0. -1 times the absolute value of 1, the absolute value of 1 is 1, times -1 gives us -1. -1 times the absolute value of 2, the absolute value of 2 is 2, times -1 gives us -2. -1 times the absolute value of 3, the absolute value of 3 is 3, times -1 gives us -3. So if you'll notice, it looks basically like you just flipped this guy upside down. This has 2 different names. It is known as a vertical reflection, because I reflected vertically, also known as reflecting over the x-axis. You should be familiar with both verbiages because we reflected vertically. We shifted, everybody just went down. And then he also reflected over the x-axis. In terms of what actually happened to the original points, that means the x's stayed the same and the y's changed sign. And that's exactly what this is noting here. So if you have a vertical reflection, that's whenever you're going down like this, that is a negative on the outside. That means your y's change sign. A horizontal reflection goes the other way. So it's a negative on the inside. That means your x values change sign. Oh, and we've got a typo on here. So keep in mind for horizontal reflection, that is a reflection about the y-axis. So for horizontal, if the original looks like this, we're going to flip over to look like that. We're reflecting over the y-axis, we're reflecting horizontally. So here, from the original graph S of t to V of t, what type of reflection happened and what would that equation look like? With the original being square root of t. Go ahead and pause the video and try to write that yourself. This was a vertical reflection, or over the t-axis, x-axis, but it's labeled as t here. So our equation for v of t would be negative square root of t with a negative on the outside. Similarly, how would I write this equation? So this is a reflection over the y-axis, or the h of t axis, if you will. It's a horizontal reflection this time, which means actually our sign changed on the x's. So for example, 1, 1 became negative 1, 1. So that negative is going to go on the inside. And I did not write that clear enough, did I? And that's exactly what this is noting. So you're going to multiply all outputs by -1, aka change the sign, for a vertical reflection. Multiply all inputs by -1, aka change the sign for a horizontal reflection. So let's actually see that in action. So here, first of all, since this negative is on the outside, what type of reflection is that? That is going to be a vertical reflection. So over which axis would that be? So that would be over the x-axis. So whose sign changes? We're going to change the sign on the y values. Or if you don't like the verbiage of change the sign, that means multiply by -1. So our x values are going to stay the same, and our y values are going to change signs. So our x values are still all at those original points, and now our y values have flipped. So instead of being at 2, 1, for example, we moved down to 2, -1 is the idea, which of course I then misgraphed. What about here? Go ahead and see if you can make this table yourself and then compare with what we get. So now this is a horizontal reflection because the negative is on the inside of the function. That means that it is over the y-axis. That means we're going to change the sign on the x values, aka multiply them by -1. So now I'm keeping the y values the same, but our x values are all going to flip signs. And that's worth sketching out for yourself. So if originally I'm at 2, 1, now I reflected over to the point -2, 1. That's what that horizontal reflection looks like. When functions have symmetry over some of these reflections, they end up being special types of functions known as even or odd functions. So let's take a look at what we mean by even and odd functions. Let's say hypothetically you wanted to reflect this guy horizontally. So the equation absolute value of negative x. Go ahead and pause this video and see if you can see what that would look like. Let's move a couple of these one at a time. So 0, 0, well, if I change the sign on the x value of 0, that stays the same. If I move the point 1, 1, that changes the sign on the x value of positive 1 to be at the point negative 1, 1. But then if I also flip the point negative 1, 1, if I change the sign on the negative 1, that goes over to positive 1, 1. And in general, if I've plugged in, for example, negative 3, negative 1 times negative 3 is positive 3, which gets us 3, which is really the same thing as the absolute value of negative 3 in the first place. Reflecting this guy horizontally folds him back in on himself. He's symmetric over the y-axis. We actually haven't changed the function. If we end up flipping all of the signs on the x's individually over here, and then flip them all individually over here, we just repeated the same function. So since they are the same, there's a special word for this. This is considered an even function, because when I reflect horizontally, when I reflect over the y-axis, it's still the same function. And that's all this is saying in words. So I'm able to check it algebraically by plugging in x is equal to negative x being how I reflect over the y-axis. And if it simplifies to the same function, awesome, we're an even function. Odd is a little different. So for odd, you not only reflect over the y-axis, you not only reflect horizontally, but then you reflect it again over the x-axis, so you reflect it again vertically. So that's like doing a double flip, essentially. So you end up changing the sign on both the x's and the y's. And there's a couple of different ways to algebraically check that. Some people plug in both negative y and negative x, and then they see if it simplifies the same way. What I would recommend doing is actually kind of doing it more the transformation way. So first I would plug in negative x, then I would multiply the whole thing by negative 1. And we'll see some examples of that. So this is visually what it means to do that. So if, for example, I first, from A to B, reflect over the y-axis, I reflect it horizontally to make B, and then I reflect it yet again over the x-axis, I wind up with C. And if you're not able to quite visually see that, I encourage you to pause the video and try to move a couple of these points one at a time. The points I would move would be 0, 0, 1, 1, negative 1, negative 1, and you'll find that you get back to the original. You either are checking if functions are even, odd, or neither by actually kind of doing this reflection yourself based on the graph, or you can also check it algebraically. And if you're going to check it algebraically, you're first going to plug in negative x for x, see if it gets you the original. If it does, it's even. Then you multiply the result by negative 1 to represent doing that double reflection, because you already reflected it once over the y-axis by plugging in negative x for x. Then multiply it by negative 1 to reflect over the x-axis and do that double reflection. And now if you're back to the original of it, it's odd. And then most functions, you're going to be like, I'm at a different function that totally didn't work. In that case, it's a function that's neither even nor odd. And most functions are neither even nor odd. So let's actually check this. So first, let's check if it's even. So if it's even, remember that means f of x is equal to f of negative x, because you're checking if it has symmetry over the y-axis, if it has symmetry when it's vertically reflected. So when we plug in negative x for x, that means everywhere I see an x, I replace it with a negative x in parentheses. And now I want to see how this simplifies to see if the result is still negative or positive. So for negative x to the third, remember that means I've got negative x multiplied by itself 3 times. Negative x times negative x gets me positive x squared, because a negative times a negative is a positive, x times x is x squared. But then times yet another negative x gets me negative x cubed, because a negative times a negative is a positive, times another negative is a negative. So I'm up to negative x cubed. And then if I have 2 times negative x, positive 2 times negative x leaves me with negative 2x. Is negative x cubed minus 2x the same as positive x cubed plus 2x? It is not, so it is not even. Since it failed the even test, I move on to the odd test, so I want to check if it's odd. So if it's odd, that means f of x is equal to negative f of negative x. So I take f of negative x, I take the result of reflecting over the y-axis, and I reflect it yet again over the x-axis. I reflect it yet again horizontally after I've already reflected him vertically. And I've already found the result of f of negative x, so let me not make too much more work to myself. I'm going to do negative 1 times my result from the previous part. That's what it means to have the negative f of negative x. It means negative 1 times this result. And then I just distributed in that negative 1. Negative 1 times negative x cubed gets me positive x cubed. Negative 1 times negative 2x gets me positive 2x. Now is x cubed plus 2x the same as x cubed plus 2x? It is, so it is odd. And if you're asked to show your work algebraically, this is exactly the process that you're being asked to show. I encourage you to pause the video and go ahead and try this next one for yourself. Is this function even, odd, or neither? If you already figure out that it's even, it's not going to be odd. And similarly, if you somehow found out first it was odd, it was not going to be even, if it's still going to stay a function. All right, let's go ahead and check. So if we want to check if it's even, that means we want to plug in negative s for s. So if we are checking that it's even here, we have negative s to the 4th plus 3 negative s squared plus 7. Negative s to the 4th, remember that means I have a negative s times itself 4 times. When I have negative s squared, that means I have negative s times itself twice. Negative s times negative s gets me positive s squared, because a negative times a negative is positive, times another negative s gets me negative s cubed, since a negative times a positive is a negative, times yet another negative s gets me positive s to the 4th. So now that became positive. Similarly, negative s times negative s gets me positive s squared, times, since a negative times a negative is a positive. And is s to the 4th plus 3s squared plus 7 the same thing as s to the 4th plus 3s squared plus 7? It is, so this guy is even. Now I already gave you a spoiler that he shouldn't also be odd, but we can formally double check that he's not if we want. So if that was the case, then this guy would still have to stay the same even when I multiply him by a negative 1 on the outside. So if I do negative 1 times the result of the previous part, because the previous part is me already reflecting him horizontally, already reflecting him over the y-axis. If I then multiply in the negative 1 times positive s to the 4th, negative s to the 4th. Negative 1 times 3s squared minus 3s squared. Negative 1 times 7, negative 7. Remember, this negative 1 is being multiplied on the outside after these s's are already being multiplied by each other 4 times. So it is not odd, just as we predicted. All right, once you go ahead and pause this video and check, is this next function even, odd, or neither? Let's check even first. So that would mean that g of x is equal to g of negative x. That means everywhere I see an x, I want to replace him with negative x. So that becomes negative x cubed plus 2 times negative x plus 9. Negative x cubed, remember that's negative x times itself 3 times. Negative x times negative x is positive x squared, times another negative x is negative x cubed. And then we still have the rest. 2 times negative x is positive 2 times negative x is negative 2x. And then we still have a plus at 9. So he is not even because this is a different equation than the original. Now let's check if he is odd. I don't know why I consider all functions to be male. I should probably sometimes be calling them female as well, but that's my own personal bias for me to work out. So if g of x is equal to -1 times g of negative x, which is the same thing as negative g of negative x, I'm just rewriting it explicitly that that's -1 times that. That means I want to do -1 times the result of the previous part, because that's already doing g of negative x. -1 times negative x cubed is positive x cubed. -1 times negative 2x is positive 2x. -1 times positive 9 is -9. So even though he almost works, because this -9 is different than this positive 9, he is not odd either. He is just going to be neither, which actually most functions are. It's very special when it has that symmetry. Last but not least, let's talk about vertical and horizontal stretches and compressions. So let's just first of all see how these look in practice. So if we're going to plug this in as particular points, let's again kind of have the original for reference. So the original starts at 0, 0, and then moves up 1 over 1 in both directions. This is the original. And now let's see what multiplying this positive 2 on the outside actually does. So if I do 2 times the absolute value of -3, the absolute value of -3 is 3, times 2 is positive 6. 2 times the absolute value of -2, the absolute value of -2 is 2, times 2 is 4. 2 times the absolute value of -1, the absolute value of -1 is 1, times 2 is 2. 2 times the absolute value of 0, the absolute value of 0 is 0, 2 times 0 is still 0. 2 times the absolute value of 1, the absolute value of 1 is 1, times 2 is 2. 2 times the absolute value of 2, absolute value of 2 is 2, times 2 is 4. 2 times the absolute value of 3, the absolute value of 3 is 3, times 2 is 6. So if we're to plot this, we have a point at -3, 6, -2, 4, -1, 2, 0, 0, 1, 2, 2, 4, 3, 6. So here there's a couple of different ways I can think about what just happened. What do you notice happened to the slope? The slope basically changed in both directions. So particularly if you're doing absolute value, actually a lot of times the most straightforward way can be to think about in terms of slope. So if originally I go up 1 over 1, up 1 over 1, now I'm going up 2 over 1, 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 up 2 over 1. So a new slope is one way to think about that. Now if I have a funkier function where the slope's not constant, that's not always the most helpful way to think of it. I can also think what happened to all my y values. So in particular, my y values went from 3 to 6, 2 to 4, 1 to 2, 0 to 0. So for all these y values, I kept the x's the same, but I multiplied y by that number out front. That's another way to think about it. The second way to think about it will be more consistent across funkier graphs, but a new slope is a good way to think about it when it comes to the literal absolute value function, since it is kind of constant in both directions around the vertex. If you notice, the vertex itself didn't move because multiplying 0 by 2 does nothing. So let's take a look at this one. We may predict, based on what we know, that we expect the new slope to be up 1 over 2, up 1 over 2 in both directions, since that would be a new way of thinking about the new slope. And again, just for reference, we might want to also put down the original of up 1 over 1, up 1 over 1 in both directions. And let's see if that's how it actually works when I plug in points and use order of operations. So if I do 1/2 times the absolute value of -3, absolute value of -3 is 3 times 1/2 gives me 3/2. 1/2 times the absolute value of -2, absolute value of -2 is positive 2 times 1/2 is 1. 1/2 times the absolute value of -1, absolute value of -1 is 1 times 1/2 is 1/2. 1/2 times the absolute value of 0, absolute value of 0 is 0 times 1/2 is still 0. 1/2 times the absolute value of 1. Absolute value of 1 is 1 times a half is a half. 1/2 times the absolute value of 2. Absolute value of 2 is 2 times a half is 1. 1/2 times the absolute value of 3. Absolute value of 3 is 3 times a half is 3/2. And if I were to plot these, granted doing the halves ones would be a little bit imprecise, but it does look like I indeed have a point approximately at -3, positive 3/2. I definitely have one at -2, 1. 1, a half is approximate as well. 0, 0 is there. So it looks like plugging and chugging our points checked out. So here, all of these y values were multiplied by a half. Or you could think of that as being divided by 2. You know, for example, the point that was originally at -2, 2 moved to -2, 2 times a half is 1. So here we multiplied y's by 1/2. Sometimes the words stretch and compress in particular are used to describe this. That's not as important as knowing the result, but the idea is that if I were to picture the y-axis as what I am stretching or compressing upon, I stretch, I move it up the y-axis when I multiply by a number that's bigger than 1. Or I compress, even though I'm multiplying by a half is effectively like dividing by 2, so I squish him down along the y-axis whenever I multiply by a number that is smaller than 1. And that's exactly what this is saying in more words. That we're talking about vertical stretches and compressions, where he will be stretched if I'm multiplying by a large number, and compressed if I'm multiplying by a smaller number. We note the absolute value because if we're dealing with negatives, remember the negative part is what reflects him over the x-axis, what reflects him vertically. So that's sort of a bit of a different thing going on. Here, go ahead and see if you can move these points yourself. What will the new graph look like if this is my transformation? This is a great example where I think it is best to think of this in terms of slope, because essentially instead of going up 1 over 1, I'm going up 1, 2, 3, 4 over 1, 2, 3 in both directions. Up 1, 2, 3, 4 over 1, 2, 3. Which is the same as multiplying by 4/3. In particular, that's easiest to see with something where it results in not a fraction. So on the point 3, 3, for example, if I multiply that y value of 3 by 3, 3 is really over 1, 4 times 3 is 12, 3 times 1 is 3, and that gets us 4. And indeed, the new point is at 3, 4. Same thing for -3, 3. If I multiply that y value by 4/3, I end up exactly where he is, which is at -3, 4. So use whatever point of view makes the most sense to you in the moment. For absolute value, I think slope is a really nice way of thinking of it. If this wasn't something as nice as absolute value, I would have gone in and tried to find points where the y value was a multiple of the denominator down here, so that it would be relatively simpler for me to go ahead and multiply it by 4/3. So let's go ahead and take a look at this. So if I have a 1/2 here on the outside, what transformation is going to happen? He's going to vertically compress, because we're dealing with something who in absolute value is smaller than 1. And the result of like, how do I actually find the values, is that you're going to multiply the y's by 1/2. You're not going to do anything to the x's though. So let's make our table. So the x's are still at 2, 4, 6, 8. And now the y's are being multiplied by a half. So 1 times a half is a half. 3 times a half is 3/2. 7 times a half is 7/2. 11 times a half is 11/2. Not the cleanest points, but they do work. So instead of being at the point, for example, 2, 1, I've compressed them down to 2, 1/2. Instead of being at the point 4, 3, I've compressed them down to the point of 4, 3.5. Right there, halfway in between 1 and 2. Horizontal stretches and compressions are not used as often in this class, but they become very important in pre-calculus when you're talking about trigonometric functions. So what's the difference here? So horizontal stretches and compressions, now your point of view has changed. So for horizontal stretches or compressions, your y's are now going to stay the same. And for your x's, you're basically going to undo to solve for x to figure out what's kind of happening here. And what do I mean by that? Well, let's actually just look at a particular example that works out kind of nicely. So I'm going to put on the point 2, 4. So if I'm doing 2x all squared in parentheses, what I want to do is figure out 2x is equal to 2 where? And then I'm going to solve backwards for x, divide by 2, and x is 1 to give me a new point at 1, 4, which is exactly what we see on the graph for parentheses 2x squared. For the other one, where it's actually a 0.5x squared, which is really a half, same idea. So for here, you would be figuring out 1/2 x is equal to 2 where? So you would undo dividing by 2 by multiplying by 2 on both sides, aka dividing by a half. That cancels out to make 1, and you're left with x is 4, which leads you to the new point of 4, 4. So for horizontal stretches and compressions, we think of it as compressing when I'm getting closer and closer and closer to the y-axis, when I'm kind of going left and right along the x-axis, when I'm going down on the x's. And I'm thinking of stretching when I'm going out on the x's. So stretching horizontally corresponds to smaller things that I'm multiplying the x value by before I perform the operation. And horizontally compressing corresponds to larger things I'm multiplying the x value by before I end up doing the operation. But really, I would think of this as you're trying to basically solve for x now that you have like a new operation going on the inside. It ends up being sort of the opposite, like it was when we were talking about left and right shifts. And that's exactly what this is telling you to do, is you want to sort of think of it that way. So let's look at this in as a new example as well. So if on the original I have the point 3, 3, on the new one that transformed to the point 1.5, 3. If on the original I had the point 6, 2, on the new one that transformed to the point 3, 2. So what happened between these two graphs? Well, if I wanted this x value on my new one to equal the x value on the old one, I would have to multiply him by 2. So here we have that r of t is equal to p of t whenever I plug in, let me think of how to phrase this. Our new function is that you are taking your x values and multiplying them by 2. So it's p of 2t, essentially. Whatever this function might be. What I do is I take the t on the r, multiply him by 2, that gives me the original on p, and now I can evaluate in the function p of t. Same thing here, if I take 3, multiply him by 2, get 6. You're good. So that's really how you should be thinking backwards. And if I knew the function on p of t and I knew r of t was p of 2t, so I'd be thinking 2t is equal to, 3 on the original, for example. T is going to be equal to 3/2 on the new. Let's think of how these two are related in a similar way. So if on g of x, for example, I have the point 2, 4, where did that move on f of x? That now moved to the point 6, 4. So to go from 2 to 6, I now had to make everything bigger. So whenever we were multiplying by 2 on the inside here, that made my x values smaller. Notice, because I was thinking, what would I have to multiply my new graph by to get the original? Similar idea here. So here, in order to get the original, I would have to take 6 and divide him by 3 to get the x value on the original. So f of x is equal to g of x over 3. Or you can think of it the other way around, that g of x is equal to f of 3x. Because once I multiply an x value on g by 3, I get f of x. Where you might be more likely to see this happen is we don't ask you too often to work backwards from the horizontal compression, although it's a good thing to think about whenever you're thinking about trig functions in the future. Let's think about how this would look like from this table. So here, if g of x is equal to f of 1/2 x, that means that I want to figure out on my new table, my y values are going to stay the same. So I still have them at 1, 3, 7, and 11. But now my x values are going to be a little different. And to figure out those x values, I'm, for example, trying to think of 2 is equal to 1/2 of what number? Well, now in order to solve for x, I'm going to multiply by 2. So x has to be equal to 4. Same thing for the next value. If I have 4 is equal to 1/2 of what number? Multiply by 2, x is equal to 8. And essentially each time I'm just multiplying by 2. That's how I would get x by itself. So for the next point, instead of 6, that would be 12. Instead of 8, that would be 16. And then this would give me my new values, where now if I do 4 times 1/2, I would end up at the original in f of x. I do encourage you to look at your textbook for some more examples, as well as ask your professor. And keep on mathing and having a good time.